Just a quick one-word summary, maybe a picture or a diagram of the review stuff, okay? So I want to know what's an arc, a minor arc, major arc, semicircle, adjacent arcs, arc addition postulate. Notice I put in the congruent arcs because that's very important for our stuff that we did today. But just quick, jot something down for yourself personally to make sure that if you really know this from 11 to a notes for what we took yesterday. What's an arc? What's a minor arc? Major arc, semicircle, adjacent arcs, and arc addition postulate. Give yourself just a quick little note. And I'm just going to use my own terminology when we're doing this. So just do what you can real quick. Just doesn't have to be this long definition, just maybe quick symbols or something like that that help you review. All right, I'll give you about 30 more seconds to write it down. All right, so with this one, guys, what's an arc? Just give me layman's terms. Don't give me fancy geometry right now. Liberty Roofing just called me. All right, anyway, with this one, what is an arc? Yeah, isn't it just a, can we just say a piece of the circle? Is that an easy way of describing it? Again, we're not doing, you know I like fancy, but this time, wouldn't we just say a piece of the circle? Does it have a beginning and an end? Yeah, it has two endpoints. So we do have a start and an end to it. How we name it's a little bit different. Okay, a minor arc. What's the easiest way to describe a minor arc? Yeah, its measure is less than what? 180. A major arc, what's so special about it? Yeah, its measure is greater than 180. And then we have, I'm just gonna go to voicemail. All right, what about semicircle? It's half as a circle, a great way of describing it, or it equals what? 180, exactly. All right, adjacent arcs. How would you describe this? Arcs that are what? Next to. Yeah, next to. Do they overlap? Yeah, they don't overlap. They're just next to each other. I was asking the grandparents, and grandparents texted, what does adjacent mean to? And they all instantly said what you just did, next to. So, I mean, it's very much a common sense. Arc addition postulate. What's the easiest way of describing arc addition postulate? I have totally brainwashed you guys. Yes! All right. Sum of the parts equal the whole. And the cool thing is if we add up all of the arcs of a circle, they always add up to 360. So it's kind of a cool type of scenario. And then we talked about congruent arcs, and we talked about like if they don't have the same radii length, a 90-degree arc in one circle is not the same thing as a 90-degree arc in another circle, correct? So we have to use the idea of congruent arcs being in the same circle or with congruent circles. Now, one thing I didn't really do with you guys that we talked about a little bit is the fact that how do you mark congruent arcs? Tick marks. We use like same thing we do with line segments. So we do it the same way. Are you guys with me on that? Okay, so for the next one on here, the next three theorems are so closely related, literally your textbook put them all together so that way they won't have to rewrite it every single time. Because look at the very first phrase here. In a circle or what? Congruent circles. So that has to happen or none of these theorems are going to work. But they really go, oh, and I forgot to grab my stuff here with it. They go pretty easily together, but if I don't write them down like this, I'm going to put them in the wrong order. So let me grab my notes here real quick. All right, so first one here, when you're working with it. In a circle or congruent circles, congruent central angles have congruent chords. So in a circle or congruent circles, congruent central angles have congruent chords. Now, let's talk about this for a moment. Remember, a chord is a line segment that connects 2 points on the circle. So you guys see segment DE and segment BC, that those are the 2 chords we're talking about, correct? Now, if I have those 2 chords, and I draw in a central angle, isn't the central angle made by 2 radii? Are you guys with me so far? So do you guys agree that this is true? Those would all be the same. And we already were told they have congruent central angles. Guys, look at triangle EAD and triangle CAB. What's so special about those 2 triangles? They're congruent by what reason? Yeah, side angle, side. My favorite. We got a little sass in class today, all right? So we have side angle, side congruence. Those 2 triangles are congruent. So therefore, what do I know about these 2 sides? They're congruent by CPCTC, corresponding parts, congruent triangles, congruent. Do you see how just that's easy to flow from there? Congruent triangles still solve everything. So the fact is then I know as a result, my 2 highlighted chords there, they're going to be the same. Pretty easy to do that, right? Let's look at the next theorem with this one, and you'll see where this goes next. And it says the following. Congruent chords have congruent arcs. Congruent chords have congruent arcs. So let's think about this for a minute. Now, this is a really almost a roundabout way, but we're going to prove it again real fast without writing the long formal proof. All right, so first of all, they're telling you that these 2 chords are the same. All right, guys, go back to the idea. Are the radii of a circle congruent? All right, so if the radii of the circle are congruent, you guys all agree with me, all 4 of those segments are the same size? So are those 2 triangles congruent again? This time they're congruent by what? Side, side, side. All right, so you guys are right on. So they're congruent by side, 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 which means corresponding parts of congruent triangles are congruent. Now, I'm not going to talk arcs because the arc's not in the triangle, but can I talk angle? What do I know about these 2 angles? They're congruent. Well, if those angles are congruent, what do I know about these 2 arcs? The 2 arcs are congruent because don't they have the same degree measure? So if my angles have the same degrees, what does that mean about those 2 arcs? They're the same. Are you guys seeing how these all relate to each other now? So basically, let's add one more little flip to this and you'll see where it goes. Let's go back with this one. How about if we do the following? Congruent arcs have congruent central angles. Congruent arcs have congruent central angles. Well, this one's probably the easiest one to understand. If those 2 arcs, let's say they're both 40 degrees, what's the measure of their 2 angles? Yeah, they're both 40 degrees. So now someone goes, where'd you come up with 40? Out of my head. It was just to give you an idea, a number instead of a variable. But doesn't that make sense? Now, basically, can I use any of these to go with it? If I gave you congruent chords, what do you know about your central angles? They're what? Which then means my arcs are what? But if I have congruent arcs, that means my chords are, and then my central angles are congruent. Any one of those 3 pairs, you know the other 2 are going to happen now. So if you memorize these, can you just build off of each other? Yeah, that's really the cool part about this. So let's add on to this real quick. Let's do some fun stuff. All right, first of all, it says the following. Segment TV is congruent to segment WS. Okay, before we go in the fact that those are just line segments, what type of line segments are those? And are they in the same circle? Yeah. So congruent chords in the same circle, what do I know? What do I get? Congruent chords, give me congruent what? Yeah, give me congruent arcs. So we know this is true. So that's what you kind of have to ask yourself. What do I have been given to me? Oh, I can apply this now. So we're going to set them equal to each other. So I get 9n minus 11 is equal to 7n plus 11. Add 11 to both sides. 2n equals 22. N is equal to, did you guys get n is equal to 11? Do we just need to plug and chug it in then? Yeah, so make sure we use correct notation. So we put the m in front when we're talking about the degree measure of an arc. So we got 7 times 11 plus 11 is going to be what, guys? 88 degrees. Yep, it's going to be degrees this time. So make sure when we talk about degree measure, it's got to be in degrees. Guys, what do you think? Easy schmeezy? Yeah, because if we know our rules, it applies really well. Look at the next thing that they tell you. They say circle C and circle J are congruent. Isn't that one of my stipulations for the theorems we just wrote about? Yeah, so they're the same. And then it says the measure of angle GCD, well, it says measure there. You guys know well, it's going to drive me nuts. All right, we know angle GCD is congruent to angle NJM. That's what I get for copying and pasting from the book. They even made a typo. All right, so I have congruent what type of angles? I have congruent central angles. So what if I have congruent central angles, what do I know about my arcs and what do I know about my chords? They're the same. So in this case, I'm talking about the chords, right? So don't I know that this and this are going to be the same? Right? So congruent central angles are going to be congruent chords. So if that's the case, we're going to set them equal. We're going to go 4t minus 6 is equal to 5t plus 1. I get 9t is equal to, did you guys get 9t is equal to, something's like 20, well, did I write something down wrong? 26, hello, 26. So it'd be 27. Whew. We didn't get the whole problem solved this time at least. All right, so what's t going to be, guys? 3, awesome. I look for the length of segment NM. Just plug and chug. What do you guys get? 16. Good stuff. What do you guys think? Easy? Isn't it really easy? Think about how simple this really is if you know the rules. If you don't know the rules, could it get really complicated? Yes. All right, look at the next one. Ray PT bisects angle RPS. The moment I tell you this, what do you guys know? I have what? I have congruent central angles. I bisect an angle. That means I better have 2 congruent angles, which makes those congruent central angles. If those are congruent central angles, what do I know about my chords? Yeah, they're equal to each other. So that's the cool part about that now. I'm just applying our theorem. So we get 6x is equal to 20 minus 4x. Add the 4x over, what do we get? 10x equals 20. X is equal to 2. Find the length of segment RT. We need to plug and chug. Did you guys get 12? All right, so RT is going to be length of 12. Now, could I be mean and put something like a factoring problem in there or something? Just don't shy away. Just do it. Use the rules. You'll be fine. Now, I like this one. The next 2 problems, and this is the reason why I like them, because I like seeing what everything and anything you can get out of here from this diagram. And so we'll probably do even more than what your book would have something on here. So on this one, it says, list what you can conclude from each diagram. So you're given a couple pieces of information first. You're given that circle Q is congruent to circle T. What does that mean? Our circle is congruent. Radii congruent, all right? And you're also given one other thing. You're given the fact that arc PR is congruent to arc SU. Start talking to me. What do we know? You said PR is congruent to what? Yep. Segment PR is going to be congruent to segment SU. Keep talking to me. What else can I assume? All right. The radius are going to be the same. And I'm going to actually just leave a little bit of space there, but that's totally correct. Can I go segment PQ is congruent to segment QR, which is congruent to segment ST, which is congruent to segment TU? Because if the triangles are congruent, isn't this true, guys? It wouldn't be a true statement if that's not the case. All right. Now, what's another thing that I know? Keep talking to me. What else do I know? Yeah, angle PQR is congruent to angle STU. All right, those should have been like the biggies. There's other things you could tell me. With what I have marked up there, is there anything else I should be able to get from this diagram? Your base angles are what? Guys, don't I have isosceles triangles here? And what do I know about isosceles triangles? The base angles are congruent. But what's so special about these triangles? They're what to each other? They're congruent to each other. So the fact is, I have those base angles that are congruent. So you actually can go a little bit further with this and tell me angle QPR is congruent to angle QRP, but that's also congruent to angle TSU, which is going to be congruent to angle TUS. I mean, that's a lot of information. If we had other points, could we even say the major arcs were congruent to each other? I mean, that's the cool part about this. We have a lot of different things we could really go. We just don't have any points to name them with. All right, talk to me about on the next one. Actually, you guys do the next one. Go, just start putting everything you know down. You guys do the next one. All right, when you're looking at this, do you get the fact you have congruent arcs? Because does congruent chords have congruent arcs? Would they also then have congruent central angles? All right, so you should have had the arcs right away, and you should have had your two congruent angles. So angle BAC is congruent to angle KJL. So you should have had these as the things you marked first. Now, what did I mark next on mine? All the radii are what? Congruent to each other. So I have all four of the radii drawn in the two circles being congruent. Can I go back to the base angles idea that we had before? Is that still an okay thing to do? A lot of people don't go there, but I think you guys can. We know that angle ABC, so this one right here, is going to be congruent to angle ACB, which is going to be congruent to angle JKL, which is congruent to angle JLK. Are you guys with me on that? So really, it's not that bad. But again, look at all the stuff you could assume when they give you like congruent circles and they just said two chords are congruent, that's it. What do you guys think? Easy? It's not bad, is it? All right, well, our next theorems, and you guys know me well enough to know I don't like theorem numbers, and I forgot to take them off, so just kind of scribble those out because you know darn well I'm not going to have you memorize what the number is when you're working with it. But I am going to expect you guys to make sure you know these theorems really well, because these are actually ones that I've shown up. I don't know if it's been as recent on standardized tests, but I've seen these on former standardized tests, on my test, if nothing else. It's going to show up. Your quiz next week, when? Tuesday. You're going to have to know this. But this is kind of a cool thing. And the reason why we say or diameter, you'll see in a second, but here's the first theorem. It says, in a circle, if a radius or diameter is perpendicular to a chord. So if I form a right angle to the chord, then it bisects the chord and its arc. So if I have a segment that's perpendicular to a chord, then it's going to bisect the chord. So these two segments are going to be the same, and it's going to bisect that arc. So I can have a lot of different congruent things as a result. Now, can we talk about the why behind this for just a moment? You guys don't have to write this down, but let's talk about the why. If I drew in that segment that's perpendicular from the center and it's perpendicular to the chord, do you guys agree with me? I could draw in an isosceles triangle. And if I have an isosceles triangle and I have from the vertex angle and it's perpendicular to the base of that triangle, what does it do to the base? That's why it works. Because I can make an isosceles triangle that works. Does that make sense? That's the why of how it happens every single time. You could also prove it by using congruent triangles, which I don't think any of you care. All right, but either one of those approaches would totally work on this one. Are you guys with me on that? So that's why. But did you also notice what I just drew in? Did I drew in the radii of the circle? Is it still there no matter what? Yeah, so don't be afraid to mark up your diagrams quite a bit. Now, the next one's just going the opposite, okay? We're going to use the converse on this. So just know this is the converse one. I'm going to go back to my green. It says, in a circle, the perpendicular bisector the perpendicular bisector of a chord is a radius, or you could say, or diameter. Now, why am I including the diameter here? Isn't the radius a portion of the diameter? Now, guys, this is a sidebar that you're all going to pay me the big bucks for someday. This is one theorem I think Jesus actually used. Because what was his profession before he went into his full-time ministry? Carpenter. Do you think he ever made anything else? Yeah, but the thing is, they're not going to have the accurate lasers and stuff like we did way back when, right? So with this one, what would he do probably? He would make the round top, right? And all he'd have to do is take a piece of string on like something that could mark, and he could easily draw the circle, and it would be very accurate. But the thing is, if you took that off, how would you know the center of like a tabletop or even a will, let's say, for instance, on there? How would you know that? Well, you could do it using this theorem, because you could draw any chord that you want. Just draw the chord. Could you find the perpendicular bisector with it? Yeah, so you draw in your perpendicular bisector. Well, what do we know about our perpendicular bisectors? They go through what? The center. Now, the thing is, I just know the center is somewhere on that line. So couldn't I just draw another chord? So literally, couldn't any carpenter in that time frame draw another chord and then draw the perpendicular bisector of it? Where would they intersect? There you go. You don't have to have fancy tools to find out like the center of a table or anything like that. This is probably more what, until basically in the last probably 50, 60 years, is what people use to find the center of round objects. So I would say this is Jesus' theorem. I have no idea, but I'm assuming he probably applied that type of theorem. Wouldn't you think? Because isn't that very practical? Because you could be able to find the halfway mark, and then you can make the square. Like we have what carpenters use what's called the square measure, and it's literally just a right angle they use to make all that type of stuff. It's pretty cool. All right, so a carpenter square is pretty easy. Now, let's apply this stuff on here. Oh, forgot to put something on here that I should. Mark your what? Okay. I've decided this semester I'm just going to write it the last few weeks as much as possible, so that way you leave my class the whole for the rest of your life. The moment you see a word problem or anything that has a shape in it, you just mark it up. Like, that's what you're going to do. It's going to be my legacy for your ACTs. It's like you're just going to mark your diagrams, and they'll be like, someday you might thank me. All right. Might. I noticed I said might. All right. With this first one, I want to know the length of segment NP. All right. But guys, talk to me. What do you know? What's the one thing you know? You know the radius. What's the length of the radius? 17. Good. So we know the radius. I'm so proud of you guys. You got that right away. The radius is 17 units, right? I just know it's 17 units. It's great. What else do I have drawn in there? I have a chord. What else? Keep going. The radius and the chord are making what type of angle? So does that make them perpendicular? So if I go through the radius and I'm perpendicular to my chord, what do I do to that chord? I bisect it, right? So the fact is, the only other thing I know is that those two are going to be the same. Now, wouldn't it be nice if I had something called a right triangle that I could use for this? Do I? What do I need to draw in? How about I draw in another way? Radius. And here's where you always draw it, guys. If you do this, this makes it so easy. If you draw in your radius always to the end of the chord, you've instantly got your right triangle that you're going to work with. And what did you already tell me that the radius was? All right, so my hypotenuse is 17. My leg is 8. Huh. What's my other leg? 15. So that means from here to here is 15, which means this one has to be what? 15. Can anyone tell me the length of segment NP? Yeah, 2 times 15, which is 30. How hard was that? Grueling, wasn't it? But what was the key thing you had to do? Yeah. If you're stuck with circles, can we just say if you're stuck anytime, always draw the radius in. And here's my hint for you. The radius to, and this is my other one, to the end of the chord. So you might have to do it so it's a perpendicular bisector, but if in doubt, draw it in. There's no one saying that you can't. All right, let's look at another one. It says find the length of segment QR. Leave your answer in simplest radical form. What are you going to do? Emma, mark up the diagram. See, you just made me happy by saying that. Yes, thank you. Mark up the diagram. So where am I going to mark it up? What am I going to do? Start talking to me. All right, so the radius is 20. So can I draw a radius in? So I know the radius is 20. What else do I know? What else happened? Yeah, I know my chord is, this time they end up bisecting each other, which is not normal, so we just take it though. But we know that the radius will bisect the chord, because remember, if I'm coming through the radius and I'm perpendicular to a chord, I get my 2 congruent segments. It bisects it. So what am I going to use? Pythagorean theorem, all right. And then I'll just have to double it, right? So I get here 10 squared plus x squared equals 20 squared. You guys are going to see a pattern pretty quickly on this one. 100 plus x squared equals 400. X squared equals 300. Guys, take the square root of that. Do I worry about the negative this time? Not this time. X is going to equal the square root of 300. Is that in simplest radical form? What is it? 10 root 3. Okay, so this is 10 root 3, but is that my final answer? No, I need the length of segment QR. So I've got to double it. Be 20 root 3. What do you guys think? Make sense? I hope so.
Like, could you use like 30, 60, 90?
If you noticed right away that you saw the pattern of the short leg being, you could have. But the thing is, I would always be cautious because you don't want to just always instantly assume on that one. Now, you will use that type of concept because sometimes I'm going to give you arc measurements. Sometimes I'm going to draw a radius in and say it's a right angle, and I might ask you for the length of stuff. You're going to have to use a 30, 60, 90 triangle or 45, 45, 90 triangle. Oh, wait, I'm going to get to those examples in a moment. But you're going to have them. Are you guys with me on that? Now, I'm going to give you one more theorem that's not official. So we're just going to call it Gregerson's theorem off on the side, okay? But I want to show you what I think you guys will think is something very common sense, all right? So here's the theorem that you need to know. Congruent chords are equidistant from the center of a circle. So congruent chords are equidistant from the center of a circle. Now let's talk about the why of that real quick. Guys, think about this. If I have a circle here, and I know these two chords are exactly the same length, so here and here. Here's my center, correct? can I draw in 2 radii real quick here, 2 radii here? What's so special about those 2 triangles? They're going to be congruent, right? Now, as a result, wouldn't the segments that come here that are perpendicular, don't those also have to be congruent as a result? So that perpendicular distance, is it going to be the same? So use that to your advantage on there. Those will be the same. So that's the why behind the theorem. It's probably more common sense, like, so the book just didn't do that, but look how easy this becomes. What do I know about the distance away from the center? They're both what? They're both 7. So what's x? Because if it's coming from the center, it's perpendicular to a chord, it bisects it. Well, they're both 3. So there goes any work you have to show on that one. Hello, x equals 3. So if you ever see that, use that to your advantage. Use that to your advantage. All right, let's look at the next one. It says find the value of x to the nearest 10th. Now guys, knowing me as well as you do you think I'm going to make this in radical form first before we go to the nearest 10th? Yeah, you know, I can't help not having the exact answer somewhere on the page. So with this one though, talk to me, how would you do this one? What would be the difference for this one? Would you draw in a right triangle? What would you guys say? Would you agree with him? Yeah, totally draw in a right triangle. In fact, that's what I'd almost yell at you if you didn't. All right, so how if I draw it in right here? Is this still going to be 3? All right. Now, what do I know about that segment coming from the center there that's labeled a length of 2? What is it doing to my chord? It's bisecting it. So here's my question. Am I going to solve for x right away, or am I going to use maybe a different variable or something? Can I call that y first and then remember to double my final answer? Don't you guys think that might be the easiest way on doing that one? But the moment you do that, what type of triangle do you have? Pythagorean theorem, right? So what is it going to be? 2 squared plus what? Equals 3 squared. At least it's nice numbers, guys. So we got 4 plus y squared equals 9. Y squared is equal to 5. I'll take the square root of it. Y is equal to the square root of 5. But what's x going to be? 2y, right? So 2 root 5. Now I'm going to be okay if you punch that into your calculator. Would you guys get to the nearest 10th? 2 times the square root of 5. Awesome. 4.5. The key with these, if you notice, is making sure you know the theorems, right? So that way I know if the radius is a segment coming from the center is perpendicular to chord, I know it's bisected. Also using the fact that all the radii of a circle are congruent, so you can use that over and over and over again. What do you guys think? Easy schmeezy? All right, I'm gonna have a little bit of fun. I'm gonna pause the video for a moment. You guys try C. You guys try. All right. With this, you're drawing in a chord, you're given an arc, and you're given one of the radii. Is there anything wrong with drawing in the radius that's perpendicular to the chord? Can I do that? All right, because we know there's an infinite number of radii. So I'm going to strategically draw which one, right? What does it do to that chord? Bisects it. Okay, great. But what does it do to the arc? Okay, if that arc is 60 degrees, guys, what's my central angle right here? What did we just make? 30 what? Now, the key thing is making sure you put the 30 in the right spot. Now can I go and find my short leg? What's the short leg? At least it's a nice number. Make sure you put it in the right location, but there's your 6. What's your long leg? Doesn't that make this segment over here also 6 root 3? So guys, x is really just 2 times 6 root 3, which is 12 root 3. All right, now you're supposed to give that to me in the nearest 10th. I like 12 root 3 better, but we're not going to change directions now. What'd you guys get? 20.8 units of a circle. How many of you were leaning that way? Any of you were thinking like 36? The moment you saw the 120, you should always hesitate and go like, can I change that into a 30, 60, 90? Like, you just kind of want to hesitate anytime you see that. But again, we've just been talking about radii being perpendicular to a chord, so we need to do it. Yes, ma'am. All right, what did you do differently? Yeah, that would also work. That would work as well. Good job, guys. Great job. All right. Oops, do we have one more over? Oh, we have to do this one first. All right, guys, talk to me. What should I mark? Can I just, do you guys agree with me that's true? Anyone want to tell me what x is? Why do I know it's 6 root 2? It's a 45, 45, 90 because the moment I have congruent legs of a right triangle, my angles are congruent, which makes them 45, 45, 90. Leg to hypotenuse, 6 root 2. All right, so give that to me as a decimal, though. 6 root 2 is approximately what? Yeah, 8.5. And I'm just going to put here as a reminder if anyone's watching the video, 45, 45, what? 90. All right, almost done, guys. So far with notes, none of this is really earth-shattering. It's just that you have to really apply what you know. All right, are you guys good with that? Like, you just have to really know. All right, with this next one here, it says find the radius and the measure of arc AB. Find the radius, the measure of arc AB. Guys, let's find the measure of arc AB first. For A, what's the measure of arc AB? It's what? Yeah, it's 120. So the measure of arc AB is 120 degrees. Why? Congruent chords have congruent what? Arcs. So that's easy. So we got 120. But now I want to find, in this case, the measure of, and I probably shouldn't have used 120, but it's just the number that's off the top of my head. I want to find the measure of the radius. What would you do? What should I always do? Draw it what? Draw it in. And aren't I going to want to do it where I know there's numbers I can use? Guys, what's your radius? Roughly what? 13? So we know our radius is going to be 13 what? Feet. It's a 5, 12, 13. Triple. Ah, so great. Here's one thing I want to add to the directions, okay, guys? Go to the, find to the nearest degree, because these are going to be weird directions and weird numbers if we don't. So find to the nearest degree the measure of the arc. All right, 2 problems left. And I'm going to ask you to go back to the exercises on your mind. But I want to know the measure of the radius, and I want to know the measure of the arc. Talk to me first. Which is going to be easiest to find this time, the radius or the arc? Isn't it going to be the radius? All right, because what do? Can I draw this in? What happens to my chord here? Bisect it. So you guys agree with me that's 3, so this would be 3. Can I go 3 squared plus 6 squared equals, I'm going to call it r, just keep it easy, r squared, r radius squared. So what do we get? 9 plus 36 is equal to radius squared. So isn't that 45? Someone, guys, double check my math. I messed up in front of the grandparents yesterday. So sad. All right. Guess who were the ones protesting the most about my mess up? My students? No, the grandparents. They go, they were so cute. They're like, oh, they were awesome. All right. And I'm like, oh, I do this all the time. Ask my students. Like, I openly confess my sins to them. I'm like, yeah, I do this all the time. I start talking and I mess up. All right, guys, what's the square root of 45? Should be 3 root 5, right? So your radius is going to be 3 root 5. All right, so that we have. But now I want to solve for the measure of the arc. Let me redraw this triangle just a little bit. I want this whole big angle, but this is really what I have. Here's my question. Can I solve for half of it? And how would I solve for half of it? I heard it louder. Okay. Right? I can't use 36 to 90 because the pattern doesn't hold. I can't use a 45, 45, 90 because 6 and 3 aren't the same size. What's the only other option, especially if I'm looking for the measure of an angle? It's going to be what? Trig. All right, so here's my question. That means I have to concentrate right now just on the right triangle part. So I got to look at it right here. But guys, which ratio am I going to use to solve for x? All right, so we're going to use tangent. Great. So I got the tangent of x degrees is going to equal opposite over adjacent. So what's my opposite? So we have 3, 6. So here, I'm going to do my inverse tangent. You can say of 1/2 or 3, 6. It doesn't matter either way. Equals x degrees. So guys, do me a favor real quick. Punch that into your calculator. Make sure your calculator is in degree mode. What'd you get? So second tan right to get our inverse tangent, our arctangent symbol. Put in 0.5 or 1/2 and give me an answer there. What'd you guys get? So you said what? Yeah, 26.57. Now, don't erase your calculator because is that my final answer? No, I want the measure of arc AB, so what do I have to do to it? Double. So the measure of arc AB is 2 times x. So when you put this in your calculator, go times 2, and what do you guys get? All right, to the nearest degree, it's going to be what? 53 degrees. So we're still having to use trig with this stuff, but I still have to use my new theorems and formulas as well. All right. Should we fly through the last one because it's using the exact same type of thing? Are you guys good with that? I am not worried about you guys solving for the radius. So are you guys good if we don't solve for the radius on this one? Are you guys good with that? On this last one, let's just only find the measure of arc AB. But do I have to approach it the same as our last one? Yeah, we're going to use the fact, really using the fact this would be extended, that this is 2. What's this side going to be? 2.5. And I'm going to be looking here for this angle, which is going to help me double it to get the measure of the arc. So my central angle is going to double to get the arc measurement. All right, what would I do? What ratio? Tangent. So I get here, the tangent of x degrees is opposite over adjacent, 2.5 over 2. Do our inverse tangent or our arc tangent. What does that become out approximately again? That's 51.34, but notice I'm not done with that because I'm really looking for the arc. How do I get the measure of the arc? We got to do what to it? We have to double it. So that's where you're going 2 times whatever this is going to be. So it rounds up to 103. All right. So the radius you just used the Pythagorean theorem for. I'm not worried about you guys going 2 squared plus 2.5 squared in order to get that. You guys would be fine. Are we good? All right. So here's what I need for you to do. If you do not have your calculator out, get it out. We're going to do a quick